All right, so today we're going to look at operations on roots, whether it be adding two roots together, subtracting, multiplying, dividing, or even simplifying or reducing roots. We're going to go through all of these in this video. But before we do that, we need to think about some properties of exponents. Because in terms of order of operations, a root holds the same priority as an exponent because it is an exponent. So it would be nice to know or refresh yourselves with some of these properties so that we can make sense as to how these things are going to work. So remember that an exponent is just shorthand for multiplication. So if I have two things being multiplied together and they're raised to an exponent, really all this means is I have that value multiplied by itself this exponent number of times. And since xy is multiplication, and multiplication is commutative, it doesn't matter which order we multiply them in, then we can say that if we reorder them so that we can multiply these x's together and reorder them so that we can multiply these y's together, then basically all we're saying here is that as long as we have one term, right, raised to an exponent, just one product of something, then that exponent can be distributed to both multiples of that term, right? This is going to be useful in a little bit. Under the same idea, since an exponent means how many times this value is multiplied by itself, then this would mean I have 3 x squareds multiplied together, and we know that x squared is just x times x. So basically we have x times x 3 times, but altogether this means that there are 6 total x's. So an exponent raised to another exponent would just be multiplying those two exponents together. Right? And if we have a fraction raised to an exponent, same idea, it's still the fraction times itself 3 times, which means we multiply fractions straight across. So on the top, we're going to have 3 x's multiplied together, which is just x to the third, 3 y's being multiplied together, which is y to the third. So a fraction raised to an exponent, we can again essentially distribute the exponent to each multiple in the numerator and the denominator. Right? So we're going to need these later, right? Because in terms of a root, as we'll see right here in a second, we need to look at this. We need to think about what a root means to tie it together here. So I think in general, a lot of people realize that if we had an x squared value, that if we square rooted the x squared value, they would cancel one another. I think this is something that a lot of people are familiar with. So if we think about what this means that if this holds a priority as an exponent, then we can say x squared is being raised to some exponent, and a lot of times people know that these things will cancel out, so we know that the result of this is just going to be x to the first, right? Now, we just got done going over that if we have an exponent raised to an exponent, that this would be multiplication. So if we think about how this root works, we can essentially say, well, 2 times some value, 2 times some value should equal 1, because if we multiply these together, we should get a value of 1 out. So what value, right, we could say, what value would we multiply 2 by in order to get 1? Well, we can undo multiplication with division, and we can say that this unknown exponent would have to be a 1/2 exponent. So a square root is the same as writing it as a 1/2 exponent. So it's just a fancy way of writing something, right? A lot of times we don't like writing things in the form of fractions, so we develop kind of ways to write it so that it's not as a fraction, but represents a fraction. We'll kind of see a piece of this from time to time. All right, so this should be kind of enough of a basis to get things going. So let's look at a sequence of values here, right? And we'll kind of go through this. Okay, so let's start off with something nice and easy, right? Because for starters, we need to kind of understand how to evaluate a root before we can start messing with it. So I think if you ask a lot of people, they'll say, well, we know that the square root of 4 is 2, right? But, why is it 2? Well, we could say that square root of 4 is the same as 2 times 2, right? And two numbers multiplied together, that's what an exponent is. So this is just shorthand, right? 2 squared is a shorthand version of, two numbers being multiplied together this many times. And we just talked about how a root and a square would cancel to leave us with just the value underneath the root, which is 2, right? Another way we can think about it is what number multiplied by itself would give us 4? Well, 2 times 2 is 4, so it reduces down to 2. But the idea of splitting it either like this or as a perfect square will be useful when we start talking about how they reduce. So it is a good thing to kind of think about, how this works out. Right? Now, square roots aren't the only ones that we work with. We could have a cube root, but a cube root has the same basis, right? If we want to think about it in terms of, 8 is the same as 4 times 2, right? And 4 is the same as 2 times 2. So this 2 is still here. Then we can say that 3 2's multiplied together would be 2 cubed. And same theory here. A cube root cancels a cube, or a power of 3, which would leave us with just the 2 underneath. Or what number times itself 3 times, right? Because this index here is 3. What number times itself 3 times would give us 8? Well, 2 times 2 times 2 is 8. So we know that the cube root of 8 is 2. But again, we can break it down and we can try to look for a value that forces that root to simplify down. That, like I said, again, that's going to be useful later to think of it that way. Because it almost seems overkill if you already knew what that value is. So let's try 12, right? Square root of 12 is not a perfect number, right? So while there is no whole number or, that we can break this down into, if this thing can simplify, kind of like if we were to simplify, 2 over 4 simplifies to 1/2, then something like this, we would want to do this. So this is where breaking it up into components is going to work here, because we can say that 12 is the same as square root of 4 times 3, because 4 times 3 is 12. Now this is where we need those exponent properties, because if we multiply two values that are underneath the same exponent, then we can split this apart. Because our exponent property said as long as we multiply values that have the same exponent, we can essentially distribute it to both products. But now, square root of 4 is the same as 2, and square root of 3 is not a whole number, nor does it split into something that would be a whole number. So square root of 12 can reduce down to 2 roots 3. So there's a couple different ways we can do this. I'm going to kind of show both methods, and then you can choose how you want to break this down. So, one method would be breaking the number down and trying to find a perfect square multiple so that it reduces away, right? And another way would be to consider the idea that if we had 3 of the same multiple to cancel out a cube root, or 2 of the same multiple to cancel out a square root, then maybe we can reduce it down that way. So another method might be to say, well, let's just try to find multiples of 12. Now, it doesn't matter which multiples you select, right? So we could say, maybe 2 times 6 is 12, right? Doing something different than 4 times 3. And then we want to keep breaking it down until prime factors, right? So 2 is a prime number, so we're going to leave him be, but 6 can break down into 2 times 3. So we've broken it down into its prime factors, but we know that a square root needs 2 of the same number, because 2 of the same number is to say 2 squared, and we know that the square root of 2 squared is just 2. So if we have 2 of the same number as a multiple, then what I'll continue to say from here on is that we can pull the 2 outside the root. Now this 3 is still a component of our value underneath the root, but he is not a perfect square, nor does he have a second 3 to go with him. So any value that we didn't pair off would stay underneath the root, as I'll continue to talk about this. So a lot of times people will like to make like a tree because maybe they're not familiar with the perfect roots and they can't just spot them from a number, or if the numbers get big, it becomes a little harder to see which values are perfect roots and which ones aren't in terms of multiples, so you can kind of just start pairing them together, right? Now this process still works if it was a cube root. We just need to consider the idea that a cube root would need a perfect cube to break down, or 3 of the same number. Now, a lot less people tend to have perfect cube values memorized as perfect squares. So a lot of times this kind of tree method, as I'll call it, becomes a little bit more favorable, because we're just looking to see how 54 breaks down. So we can say, 54 breaks down into, 2 times 27? But we're looking for prime numbers. He's good, so he can't break the 2 down. But 27 can break down into 3 times 9, and 9 breaks down into 3 times 3. So we've broken it down into its prime components, right? We're not interested in the 9 anymore, because the 9 broke down. We're not interested in the 27 or the 54, because they broke down. Only the values that we broke them down to. But since it's a cube root, we're looking for 3 of the same number to pull a value out. So since we have 3 3's, which is like 3 cubed, we know that a cube root and a cube would cancel, right? So kind of like I was saying, if we have 3 of the same number, because it's a cube root, we can pull 1 3 outside the root. But any pair that doesn't, any value that doesn't have a triplet of values would stay underneath the root. So this 2 here is going to stay underneath the root. Remember, it's a cube root, not a square root. And there we go. We've reduced it down. Right? So an index of 3 means we need 3 of the same number. Index of 2 means we need 2 of the same number if we're going to try to break these down and reduce them. So we were able to reduce the root. It wasn't a perfect root. He wasn't a perfect root, but it did reduce. So that's what we can reduce or simplify these things. All right, let's try a bigger one. So maybe we have a number outside already. That's fine. Our concern is the root and if it reduces, right? So again, it doesn't really matter how we break this down, right? We can just say, let's find multiples that make 180. Now, whichever numbers, come to mind is really all that matters. When I look at this, I see a 0, so I think 10, right? 10 times 18, 10 times 18, not 180, right, is 180. And then I want to keep breaking these down. So 10 can break down into 5 and 2. 18 can break down into 2 and 9. Now I'm going to stop here because I want to talk about a few things, right? You can break them out as much as you want and then just look for pairs, because since it's an index of 2, we're looking for pairs. So here I'm going to stop here and just explore what you can do. So if you see something, you can kind of just go with it. So for starters, since we have a pair of 2's, we know that we can pull a 2 out. Now, anything that gets pulled out gets multiplied, because remember, these are products. So since he's a product already, and I'm pulling this 2 out because it's a multiple, then all these things that are outside get multiplied together. So if I find 2 of the same number, I can pull 1 out, right? Now, the 9, if we want to think about it as we're looking for perfect roots, 9 itself is a perfect root. So if we want to say, hey, the square root of 9 is 3, we can pull a 3 out. Or you can break down 9, because you know 9 is 2 3s, and there's our pair. Now you can pull it out, however you want to do this. So if you break it up and you find a perfect root, then you can just stop and pull him out as a 3, because square root of 9 is 3. Or you can just break it down as much as you want, or can, not really as much as you want, and then look for pairs. Right? So we were able to pull multiple pairs out. We pulled a 2 out. He's going to be multiplied. We pulled a 3 out. He's going to be multiplied. But don't forget we have this 5 left over. So a 5 is left underneath the root. We have these 3 numbers being multiplied together. Right? So we got 3 times 2, 6. 6 times 3 is 18, which is on the outside. So we pulled some numbers out. Some numbers were left in. There's our reduced root. All right, let's try another one. So here, again, it's a cube root, which is fine, right? 72, we're going to break down 72 as much as we can, right? First thing that comes to my mind, 8 and 9. Now you might say, ooh, 9 is a square root. But remember, we're looking for cube roots. So we need 3 of the same number, right? So 9 breaks down into 3 and 3. So the only thing that this is going to be useful with is if 8 had a multiple of 3, right? But 8 breaks down into 2 and 4 breaks down into 2 and 2. So even though we have 2 3s, we don't have a third one. So these guys are going to stay there. But we do have 3 2s. So we can pull these 2s on the outside. Remember, one of them, we need 3 to pull 1 out. But these 2 3s are left underneath the root. It's a cube root. And we just want to multiply them back together. Anything that didn't break down to have a triplet here for this cube root, we don't want to leave it as 3 times 3, because we know 3 times 3 is 9. So we fold the 2 out. The 2 3s stay under. And this thing reduced down to this one. Right, so if we have cube roots, we have square roots, we can reduce these down. Right, we'll practice these as we move along. Right, let's go into starting operations. Right, so let's start with the easy one. Adding and subtracting tend to be pretty straightforward. Okay, the best way to think about this is we have the roots, and the number in front is like, think about it as a quantity. Right? How many root 2s are here? I have 5 of them. How many root 2s are here? I have 9 of them. So in order to add or subtract roots, the root itself needs to be identical. Because if this is a quantity to these roots, and I want to try to add them together, I can add the quantities as long as they're the quantities of the same value. So 5 of them plus 9 of them, right? We can just add these together. So when we add the roots, there's still going to be some number of root 2s, right? There's still going to be some number of root 2s, but 5 of them and 9 of them is 14 of them. So we'll have 14 root 2s is the sum of them. Now, if we could reduce root 2, we would, but in this case, we can't. Right? So same thing if this was a cube root. Again, the roots need to be identical in order to add them together. Now here, there's 8 of them. Here, there's no coefficient here, but you can always think of it as like a 1 if you wanted to. We have 1 root 11 minus 8 root 11s would be negative 7 cube root of 11s. Right? And 11 is prime. It's not going to reduce. Right? So remember, adding and subtracting roots, the roots have to be identical, totally identical. If they're not identical, we can't add them together. So let's try something else. So here we go, we got 3 of them. Now none of them are the same, so we definitely can't add them together. But 75 is a big number, 12 is a big number. Maybe these can reduce. 3 don't reduce, right? So we're going to leave him alone. But we'll look at the other 2, right? At the least, we can reduce them, right? So we can say, well, 75, what's that? 25 times 3? Right? And then 25, you can either say is a perfect root, or it breaks down, so I can pull a 5 out. So root 75, that reduces to 5 root 3. Now this guy don't reduce because 3 is as small as it's getting, so I'm just going to leave him alone right here, right? And then we can look at 12. 12 breaks down into what? 4 times 3. 4 breaks down into 2 times 2. So again, we can pull a 2 out because we have a pair. There's already a number outside, so we're going to multiply. Remember, it's still going to be a plus, right? So 3 times 2 is 6. Don't forget this root 3, or I'm sorry, the 3 stays underneath the root, right? So the roots weren't identical. Some of them looked a little big. We were able to reduce them. Now that we've reduced them, if they can add together, now we would, right? So now all the roots are identical. So we can say, well, we have 5 of them, right? Minus 11 of them, plus 6 of them can all add together to make some number of root 3's. Now, 5 and 6 is 11, so 11 minus 11 is just 0. But, 0 times the value is just 0. So all of these essentially just cancel out. Right? So if they if they can't add, we try to reduce them. And then once we have them reduced, whichever ones can be added together, we would add them together. If we can add them all, great. Right? So like if root 12 couldn't reduce, for instance, right? So like if we had something like root 5 plus root 12, right? Root 12 reduces, right, to 2 root 3, but I still can't put it together with root 5 because the roots aren't the same, so there's really nothing I can do there. I would have to just leave it, okay? So you might be able to reduce them and then they can't add. That's fine. Do what we can. So let's try multiplying, right? So multiplying is a little easier to deal with because since the exponents are the same, we can think about back where we had our exponent properties, right? Because if the exponents are the same, then we can multiply them together, right? So here, when we had 2 things that had the same exponent, we can essentially multiply them together if we work backwards to say that that same exponent is multiplied to the product of these 2. So this works out nicely because we can say, well, both of these can just be multiplied together and say 10 times 2 is 20, right? Now, if it reduces, we would want to reduce that. Now, if we reduce it, we can say, well, 20 is, we can break it back down into 10 and 2. So what I'm going to kind of suggest here is that if we wanted to multiply 2 roots together, we can just put them underneath the same root and say, let's reduce these. So instead of putting 10 and 2 and making 20, and then breaking 20 back down into 10 and 2, we can just take the 10 and the 2, put them under the same root, and then just continue to reduce as we normally would, right? We can say we got 2 2's, right? So we can pull a 2 outside the root, and this 5 is left underneath. So we pulled the 2 out, the 5 doesn't have a pair, so he's going to stay underneath the root, and we were able to multiply and simplify. All right, so let's try another one. So this is multiplication. So we're multiplying this guy times this guy. Now I can't multiply roots and non-roots together. Right? Same thing here. I can't multiply roots and non-roots together. but everything is being multiplied. So the order which we multiply doesn't matter. So I could multiply these two together, because I can actually multiply constants together. So I can say negative 4 times 3, right, is negative 12. And then we can multiply roots and roots together, right, just like we did here. Now remember, 15 times 21 is some big number, and once we put it together, we're going to try to reduce it down. So instead of figuring out what 15 times 21 is, I'm just going to put 15 and 21 underneath the same root, because whatever that product is, I'm going to want to break them right back down. And then I'm just going to go from here, right? I can break down 15. What's that? 5 times 3. I can break down 21. 3 times 7. And then we have this pair, so we can pull that pair out. Now again, he's already got a 12 out here, so we're going to multiply this 3 by what's already out there, right? So negative 12 times 3 is negative 36. Now 5 don't reduce, 7 don't reduce. So these guys go back underneath the root, so it's still a square root, and 5 times 7 is 35. So here we go. That's as much as we can break this down. So things on the outside, we can multiply non-roots and non-roots. We can multiply roots and roots. We cannot multiply roots and non-roots. Right? But there's no sense in multiplying 15 and 21. Make it big, break it right back down. Right? Let's make life easy on ourselves. Right? All right. So let's look at this one. So nothing different. The index of the roots need to be the same, because that's the exponent here. So since they're both cube roots, I can multiply the things underneath the cube roots together. Now there's a 2, and I guess I could say a 1 if I wanted to. So we could put the 2 and the 1 together to say 2 times the cube root of, now I'll put the 6 and the 45 together, but again, I'm not going to multiply them, because again, I'm going to break them right back down, so that doesn't matter. Right? And then I can just start reducing them. So we know that 6 is 2 times 3. We know that 45 is what? I'll say 9 times 5. 9 breaks down into 3 times 3. Since the index is 3, we need 3 of the same number. Remember, we don't care about the 9. The 9 broke down, right? So we got 3 3s. So we can pull a 3 out, can't we? And then we got 1 2 and 1 5. So no triplets of these. So these guys are going to stay underneath. So on the outside, we have 3 times 2 is 6. It's still a cube root. Don't forget to, sometimes we'll write a square root. We kind of get in the habit of doing that. It's a cube root. 2 times 5 is 10. We know that this doesn't reduce because there's no 3 values that are the same. So we know that 10 will not reduce any further than it already has. Right? All right, let's look at one more of these multiplying here. All right, so got a lot going on, right? Well, let's think about this. We got square roots, cube roots. I can't multiply roots, square roots, and cube roots, because his exponent is a half. This guy's exponent would be like 1/3. So since the indexes aren't the same, I can't multiply them together. But I can multiply these two together. So we can say that 24 times 30 underneath the same root, because we do want to reduce them. Now, we do want to try to reduce this guy, so I'll come back to him, right? But he's definitely not going to be multiplied together. So I can break down 24. So what's 24? What do we got? 4 times 6, right? And then we can say 4 is 2 times 2, right? 30 is also 6 times 5. So I'm just going to say, look, I got 2 2s. I can pull a 2 out. I got 2 6s, right? I can pull a 6 out, right? I don't have a 4 because the 4 broke down into 2s, right? So I got a 2 on the outside and a 6 on the outside. So 2 times 6 is 12, right? And then don't forget the 5. He's still hanging out underneath the root, right? Now, let's try to break down this cube root. Since it's a cube root, we're looking for 3 of the same number, right? First thing that comes to my mind would be 4. 4 goes into 48 12 times. So we can say 12 is 4 times 3. I can't pull the 4 out because remember I need 3 of them, right? But a 4 is 2 times 2, and this 4 is also 2 times 2, right? So I don't got the 4s anymore, but now I do have 3 2s. So I can pull a 2 on the outside. It's still a cube root, right? And this extra 2 and this 3 still left over, so cube root, right, of 2 times 3 is 6. Right? So I can't multiply these roots together. Right? So I'd have to leave it as, root 5 times, cube root of 6. I mean, technically we can multiply the 12 and the 2 together, though. So I mean, if we wanted to, we could say, well, 12 and 2 is 24 times root 5 times cube root of 6. Right? If we had something like that, I mean, that's as far as we can go. The roots don't reduce. We had multiples on the outside. Those could multiply together, right? So there's not much more we can do there. That's as far as we can take this. Right? All right, let's start taking a look at dividing. So for dividing, same kind of idea, right? We know that if we had a fraction that had an exponent, we can essentially put the exponent on the top and the bottom. So we already have an exponent on the top and the bottom. So just like if we had this, we can work backwards and put the whole fraction underneath the root if we wanted to. So that would make our life, a little easier in this case, because if we put these back underneath the same root, right, like this, then we can actually reduce 18 over 2, right? 18 divided by 2 is 9 over 1, but I don't really need to say over 1. And then square root of 9, that's a perfect square. That's just 3, right? So we can just simplify this down. So as long as the index, again, the index and the root, these are both square roots, we can put the square root, either, distribute it to the top and the bottom if I work from here back to here, right? Or put them back together to make one root. And in this case, it works out nicely. Right? So just be aware of kind of what we have to work with. Right? Let's try this one. Now, there still is a root on the top and the root on the bottom. Right? So if we wanted to, we could say that this whole thing, 15 over 6, but 6 doesn't divide into 15 evenly, but it can reduce. We can say that, 15 and 6 both have a common multiple of what? 3, right? So this thing could reduce down to 3 goes into 15 5 times, and 3 goes into 6 2 times. But a square root of 5 over 2 is as far as this fraction is going to reduce, right? Now we can still think of this as root 5 over root 2. So if we wanted to, we can say, look, 15, right, is divisible by 3, right? That would be root 5. And 6 is divisible by 3, which is root 2. So if we want to just jump from here to here and say, we can divide them out and simplify it, that's fine, right? Otherwise, you can put them together, simplify it down, break them back apart. Now, a fraction is never considered simplified if there's a root in the bottom, right? We would like to have a rational number in the bottom. So what we're going to do is a process called rationalizing the denominator. We would like to have a rational number, which is either a whole number or a fraction, right? So since there's a root in the bottom, that's technically not considered simplified, even though 5 over 2 can't simplify any further. So to rationalize the denominator, our goal here is to make this look different, right? So kind of like if I wanted to add 2 fractions together, we would say, well, we can't add them together unless they had common denominators, right? So the least common denominator would be 6. And we'd say, well, if we multiply the top and the bottom by 3, then 3 over 6 is the same as 1 over 2. So we basically just made 1 over 2 look differently, but have the same value. So this is essentially what we're going to do right here. We can say, well, we can multiply the top and the bottom by something to change the way it looks. Now our goal is to not have a root on the bottom. So in order for the root to go away, we would have to multiply by something else. Now we can't multiply roots together with something unless it's another root. So whatever I'm choosing to multiply by had better be a square root, because otherwise I can't multiply them together, right? Because I can't multiply roots and non-roots. Now, we said that roots reduce if we had, since the index is 2, 2 of the same number. So right now we have 1, 2. If we multiplied by another 2, right? Then this would be, square root of 2 times square root of 2, which is square root of 4. And square root of 4 reduces. So we went from having a root, which we didn't like, now to having a non-root, which we do like. Right? So, but kind of like here, if we multiply the top by something, we have to multiply the bottom, or vice versa. So since I multiply the root 2 on the bottom, I got to do it to the top. Right? So we can say root 5 times root 2 is root 10, right? Which is fine. Now, does square root of 10 reduce? No, because 5 times 2 made 10, and 5 and 2 don't reduce any further. So root 10 is as low as this thing goes. Now, roots on the top are fine. It's roots on the bottom that you got to be concerned with. So if we have something and we're simplifying it down, and we have a root on the bottom, we're not going to be considering that that's simplified. So what we're going to do is rationalize this denominator. So there we go. We have a reduced root, no root on the bottom. That's fully simplified. So let's kind of extend this and kind of put some things together here. So let's look at this last one right here. Right? Now remember, roots and non-roots can't multiply. Right? Roots and roots can multiply or divide. Same thing with the non-roots, right? So what I would suggest here, instead of trying to work with these big numbers, is if the values on the outside of the root can simplify down, that would make our life easier. If the things on the inside of the root can simplify down, again, smaller numbers, much easier to work with than bigger numbers. So 3 divides into 3 and 6. 3 goes into 3 one time. 3 goes into 6 2 times. Now, 35 and 15, those are both divisible by 5. So we can say 5 divides into 35 7 times, right? And 5 divides into 15 3 times. So we still got a root on the bottom. Not great. The root on the top, we don't care about him, right? We don't care about the 2. It's this guy that we care about. So we want to try to get rid of him. So again, if we multiply the top and the bottom by something, that's acceptable. I don't care about the 2. If I multiply by a square root, then I can multiply these together. I have 1 3. If I multiply by another 3, then I'll have a perfect square, right? So if I multiply it to the bottom, got to do it to the top. So let's work at the top first, right? I don't care about that 1, right? 7 times 3 is 21, right? On the bottom, we can multiply the roots together to make root 9, but we still have this 2 as a product that can't be multiplied together. So we got 2 root 9. But square root of 9 is 3, so we have 2 times 3 on the bottom, which is 6. So multiplying these two together, essentially makes the 3 because it reduces the root. So a lot of times people will just say root 3 times root 3 is 3, and that's acceptable because it's root 9, right? Square root of 21 doesn't reduce because that came from 7 and 3. So the root on the top we don't care about. Root on the bottom is gone. We can't simplify roots and non-roots. So if you're thinking, ooh, a 3 can go into 21 and 6, I mean, that's true, but they can't go into both the root 21 and a non-root of 6. So this is as far as we can simplify this down. So just keep in mind, going back through it, indexes have to be the same in order to multiply or divide, right? For adding and subtracting, the roots have to be completely identical, right? Can't multiply roots and non-roots. We can divide roots. We can divide non-roots. So there we go. We simplified. All right.